now I'm already been back to Singapore. Yeah. So this presentation basically is what I have done in my master's thesis. So just looking at the title, I just need to state upfront, I did not perform any experimental research for this topic, but it is just basically is the scoping review of the fixed fire suppression system for the lithium-ion batteries. So my presentation will cover the following points: objective background, methodology, results, discussions, conclusion, and the future works. So in my master's thesis, I conducted a systematic scoping review of past research data on the fixed fire suppression system for the lithium-ion battery. So the literature review results gathered from those published papers, journals, technical reports were then analyzed and discussed the effectiveness of the fire suppression system, and also all the different kind of the extinguishing agents, as well as their potential the field applications, especially for electric buses and the battery energy storage system. Why these two but not other smaller system is on these two field applications, there are available space to install the fixed fire suppression systems, but not for those electric scooters, electric cars, where there isn't any luxuries of the space to install the effective fixed fire suppression system. Okay, here I will talk about some brief background informations on the lithium-ion battery. So I believe some audience here may have much more experience than me on the lithium-ion batteries. So I take this as a sharing session with all the audience or some experts here. So maybe you can point out something at the end of my presentation for our discussion. So basically, what is the lithium-ion battery? So this picture illustrates the basic components of lithium-ion battery cells, which are anode, cathode, the separators, and also the electrolyte. So when a battery is in a charging state, the ion flow from the cathode to anode. When the battery is in use, the ion flow in the opposite direction through the electrolyte. So the function of the separator is to prevent the contact of the cathode and the anode. So basically, if these two electrodes come into the contact, we call it the internal short circuiting. In terms of the shape of the battery cells, there are three typical shapes: cylindrical, the prismatic hard case, and also the soft case we call it pouch. And there are different type of the lithium-ion batteries differentiated or categorized by the chemistry of the cathode materials, which are listed here. So the first two types, the lithium nickel manganese cobalt oxide and lithium iron phosphide, are the most commonly used lithium-ion batteries nowadays. So in terms of the application of the lithium-ion batteries, it is ranging from the consumer electronics, such as mobile phone, laptops, to the transportation equipment, such as electric scooters, bikes, cars, buses, and other heavy industry application, like the energy storage system for the green energy generated from the wind, hydro, or solar. So the lithium-ion batteries have the following benefits, like lightweight, high energy density, the long battery life, fast charging, and high efficiency. So today, the lithium-ion batteries serve as the green energy carrier and play an important role in reducing the global carbon emission. So in the later discussion, the fixed fire suppression system, I went go through or potentially be applied on the electric buses and the energy storage system because, as I mentioned earlier, there are space available to install the suppression system. So what are the main problems associated with the lithium-ion battery? So I believe most of you know the term thermal runaway. So thermal runaway basically is the internal chemical reaction due to the abuses condition like mechanical abuse. For instance, there's a crash, there's a mechanical damage to the battery, the electrical abuses, and the thermal abuses. All these abuses actually contributing to the damaging of the separators. So once the separator been damaged, there's an internal short circuiting, which leads to the rapid temperature increment. And when the temperature increase drastically, the cathode material will be decomposed, which will release the oxygen. The electrolyte under the high temperature also releases the flammable gases. Therefore, the three fire elements, the energy, oxygen, and the fuel, all are present. So a combustion condition is met. So when the combustion condition is met, fire will initiate from the first damage the battery cell, leading to the heating or thermal abuse of the adjacent batteries. So this is how the thermal runaway propagates to the adjacent battery cells, to the modules, even to the racks, so on and so forth. So here are the two examples of fire incident. One is from the electric bus depot. So when the buses are in charging, so there's a fire occurred from one of the buses, and subsequently spread to the adjacent buses. Then the other example is the one of the solar panel system station in South Korea. So there's a fire from a battery energy storage system. So for this, I listed some of the common fire suppression systems that has been tested or been experimented in the lithium-ion battery fire. So which consists of this basically 1 to 9, the sprinkler system, water mist, with and without additive foam system, no wet inner gases, aerosol system, dry powder, and the AVD. AVD is a special the extinction medias which actually cover over a battery when it is melt. So I also categorize the working principle of each systems. For instance, number 3, the water mist system with additive. So it has the function of gas cooling, reducing adiabatic flame temperature, smothering, which means when there are a lot of water condensation being deposited on the surface, it actually will cover over the fuel surface. Also, the surface cooling, the chemical inhibiting, and also the suffocating. So why I use this as example is because the water mist system with the additive, it actually has all the functions of the fire suppression, which later on I will explain. And also the literature result from the researchers appear to be like water mist with additive. So far, it could be considered one of the most effective extinction agents. Okay. Okay, so the methodologies that I used for my scoping review follows this Prisma SCR framework. The full name is Systematic Reviews and the Meta-Analysis Extension for Scoping Reviews. So this frameworks actually provides a guidance for a systematic review of relevant research in a topic or area of interest. So in my thesis, I formulate 4 steps. So the steps number 1, I use the keyword search such as fire, flame suppression, extinguishment, lithium-ion battery from 2 popular science database, which are Scoopers and the Web of Science. So these two science database actually cover most of the research papers from the fire science community. Then the keyword search are applying on the field of the title of the journal paper, the abstracts, and also the keyword indexing. The search, I didn't set any start date, but it was cut off on 26 March 2023. So it's sometime like in the two-third time frame throughout my thesis. So from the step number one, it gave me about 425 publications after removal of the duplications from two database. So in the step number two, I performed the title screening to exclude those irrelevant titles. For instance, the title only focus on the battery compositions, the characteristics, passive fire protection, or the firefighting robots, which are actually not related to what I studied. So after the filtering in step number two, the number of the papers that going to be reviewed is reduced from 425 to 167. So for the step number three, I went a little bit further to read through the abstract and also quickly run through the main text of the paper. So same thing, I included the relevant papers and also excluded the irrelevant papers, and also to exclude those papers are not in the full, not in English. Like for instance, the South Korea actually also published quite a fair bit of the papers, but those are in Korean, so those papers were not included in my study. So after that, another half of the papers being filtered off. So after that, in the final step, step number four, the full reading, the full assessment of the complete papers are performed. So during the full reading, the citation search also been performed. That means I checked through what are the relevant references has been referred to in these papers. So after I identify these additional papers, the same process look through again. So finally, I have a final 85 the papers and the technical reports and the white papers move on for my full assessment. Okay, so from the 85 publications, 20 review-based publications, and the remaining 65 are experimental-based publications. So from the 20 review-based publications, it served as the counter check for me and to confirm that I did not miss out any major publications in my scoping review. So this graph um, shows the research trend of the fire suppression of lithium-ion batteries from the earliest research you can see from 2013 until the March 2023. So at the beginning of the research, the bar shaded in orange actually represent the US. So US was the first one who started the fire experiment on the lithium-ion battery in a small scale. Basically, that was from NASA. But subsequently, from 2018 onwards, China, the blue bar represents China. So from 2018 onwards, actually, China occupied the most of the research experiment on the lithium-ion battery fires. Then the rest are actually minority. Like for instance, the European. Actually, this is the represented in green bar, which actually is the summation of the research from all the different European countries. Okay, so from the 65 experimental-based publications, I further categorized the the different level of the experiments based on the battery configurations from small scale, the cell level, module level, to the large scale, the electric vehicle pack level, and the battery energy storage system, the rack level experiment. So the interpretation of the battery configuration is the most basic unit of a lithium-ion battery is a cell. So after that, the multiple cells are connected together to form a battery module. So sometimes the large battery cells also can be grouped directly into the battery pack. Those are in some cases applicable for the electric vehicle application. So from the battery module, multiple battery modules will then be integrated to form a battery pack or battery rack. So actually, the experiment actually being stopped here because these are the full scale the battery system already, which I believe as so far as of today, there were no researchers to conduct experiment using the complete scale the battery systems for the fire suppression system experiment. So this kind of the integration actually is to build up to get the required capacity and the wattage of a battery system. So as you can see here, the small scale, the cell level research experiment actually the most of the research focuses on this. There's only a handful of the experiments are conducted for the large scale, like EV pack level and battery energy storage rack level. So there's also one unique case of the warehouse storage. This is just for the completeness of my scoping review. That's why I also listed here. Okay, so for the results and the discussions, the first started with the cell level experiment. These are the two typical experimental setup for the cell level experiment. So basically, the battery cells are housed within a testing chamber. The difference between these two is this one is with the explosion-proof tank. This one is without the explosion-proof tank. So for both experimental setup, the battery cells has direct exposure to the extinguishing agents when this is discharged over the battery cell. Okay, from the cell level experiment, more than 20 different extinguishing agents are tested. So which include the water-based, gas-based, powder-based, and some synergistic agents. So what is synergistic agent is basically is a combination of the two different agents to improve the performance of the single agent. So as you can see from the graph here, the water mist with additive water mist, and also this C6F12O, which is actually refers to novel gases, attract most research attentions. Even this new type of the synergistic agent also work around with around the water mist and the novel to actually improve the performance of the single agent. So I believe now the researchers has entered into this area is aimed to improve the performance of either this or this. The key findings from the cell level experiment. So basically, as mentioned earlier, the lithium-ion battery cells in the cell level experiment are exposed directly to the extinguishing agents. Therefore, all the tested agents, being the water-based, gas-based, or powder-based, all are able to suppress the battery fires, except for the carbon dioxide when handling high capacity NMC batteries. But of course, for the low capacity NMC batteries, CO2 can also do the job. So from the experiment, I also drew some conclusion that the fire suppression, to suppress the visible fire, it is not a solution to mitigate the thermal runaway. To mitigate the thermal runaway, the cooling effect of the extinguishing agents is very important. Therefore, from the more than 20 different extinguishing agents, I come out this table to rank the cooling effects from high to low, from left to right. So how to interpret this table is, for instance, based on this line here, that means water is more effective than foam. Foam is more effective than water mist, AVD, then the NOVAC, the inner gases in this sequence. Likewise for the other combinations in this manner as well. So from what I found is the water-based agents are the most effective in cooling, and the cooling is the key factors to mitigate the thermal runaway for the cell level experiment. So for the module level experiment, in the module level experiment, this is the typical setup. So basically, the battery cells are housed within the battery module box. So the extinguishing agents is applied over the module box without a direct reach to the battery cells within the box. So as you can see from here, once the extinguishing agents is discharged, so inevitably it will be blocked by the module box. So as in the degree of the penetration is largely depends on the ingress protection rating of the module box. So the cooling effect that I mentioned earlier for the cell level experiment may or may not be applicable for the module level experiment here. And one additional point is the material of the module box is also play a part. So for instance, if kind of the module box is combustible, so if the fire happen, if the fire able to melt the module box, that means it will create some space for the extinction agent to seep through to reach the battery cells, which may also help in terms of the cooling and also the internal fire extinguishing for the module level experiment. Okay, so these are the tested agents for the module level experiment. So the two with the highest one, mist, high pressure and low pressure water mist, and water mist with the additive. Those are others experiments are using fire ice, the foam, the sprinkler system, nitrogen, and the aerosol. Okay, the key findings from the module level experiment. Basically here, in the module level, external fire extinguishment is totally possible because if the fire burn out the let me burn out and also appear outside of the module box, when it get in contact with the extinguishing agents, the agents will be able to put out the fire. However, the internal fire extinguishing is basically largely depends on whether or not the agents could penetrate and reach the battery cells. So this likewise goes to the cooling as well. So if the extinction agents cannot reach the battery cell, basically there's little or basically no cooling to the affected battery cells. So basically, it cannot prevent the thermal runaway propagations for the battery cells within the module box. So similarly, whether or not the water-based agent in the module level experiment still perform the better cooling effect compared to the inner gases and the aerosol. One publication even suggested if the gas-based or aerosol-based suppression system is used, water-based suppression system is always recommended to be used as a backup system for that. Okay, so coming to the electric vehicle pad level experiment. So in this experiment, the multiple battery modules or large battery cells are housed within a battery pack box. So this is a pack box. These are the battery module or battery cells within the black box. So for the EV pad level experiment, most of the experiments are using the direct internal injection methods, meaning the extinction agents, the tubing has been connected into the box directly, so the agents can be discharged within the pad box. There's also one experiment is to just for the purpose of comparing the result, it used the external spray. That means the agents applied over the pad box. So for the external spray, for the EV pad level experiment, this is similar to the module level experiment that I explained earlier on. So the tested agents in the EV pad level experiment, the NOVAC gas actually is the most tested agents. So why is it so? Is the possible reason that I can think of is the space limitation on electric vehicle. So if the water-based agents is used, it requires more spaces than the gas-based agents. So therefore, the NOVAC gas has been mostly tested. Then the rest, like the water mist, is like just one or two experiments on it. The nitrogen is also just one experiment on it, probably because the researchers already knew the NOVAC gas will have better cooling effect than the nitrogen inner gas. The key findings from the EV pad level experiments is the first one for the electric buses, the possible maximum carrying capacity of the extinction agents can be like up to 13 liter. For the direct internal injection, all tested agents could put out the fires except for the high expansion form, which is repelled by the vent gases releases from the damaged the battery cells. So similar to the cell level and module level experiment, the water mist with foam additive has the best cooling effect compared to the rest of the tested agents. And the gas-based agents are least efficient in terms of mitigating the thermal runaway due to the poorer the cooling capacity. So these are similar to the cell level experiment key findings. So for the external spray, it can only put out the external flames. So there's little or no contribution to the internal cooling. So this is similar to the module level experiment. So coming to the battery energy storage, the red level experiment. So this is the typical setup. So basically all the battery modules are housed within a battery rack. So in the experiment, either single or multiple battery racks are, are located normally in an ISO standard container. The extinction agents being applied on top of the battery racks. So you can see from here, if the lower tier, that means if the battery module caught fire here, the extinction agents may or may not be able to reach the module that has already been blocked by other modules. So this could be one of the main problems in the rack level experiment. So the tested agents been performed in the rack level experiment are this. So basically here, the sprinkler with and without additive, quite a few of the researchers perform the experiment using sprinkler. Others perform the experiments using the low pressure, high pressure water mist. So likewise, the NOVAC gases, inner gases, aerosol, and the AVD. Then there's also two experiments using the direct internal injection methods. Okay, so the key findings for the red level experiment. In the red level experiment, the primary aim is to reduce the module to module or prevent the rack to rack thermal runaway propagation, but not to mitigate the cell to cell thermal runaway propagation, because from the earlier illustration you can see basically the cell is within the module box. So to prevent the cell-to-cell thermal runaway propagation basically is not possible. So the external fire extinguishment is not fully, it's only a few selected agents can do the job. Like for instance, the high pressure water mist, the NOVAC and the inner gases were able to put out the external flame. In terms of the mitigation of cell-to-cell thermal runaway propagation, as explained earlier, it is not quite possible. Also, another key findings is the early activation of the extinction agents is always preferred. This is to discharge the extinction agents as early as possible, so as to control the fire situation at the early stage instead of control the fire station at the very late stage where the thermal runaway has already propagated to the adjacent modules, adjacent racks, which will make the whole situation is more difficult to suppress. So likewise, with the EV pad level experiment, the direct internal injection method is always it is always more effective, but it's rarely tested. And the water-based agents have shown the better cooling effect compared to the gas-based and the powder-based extinguishing agent. Okay, so for the completeness, the warehouse storage experiment, it is a unique experiment. So in the warehouse storage experiment, the battery cells are stored in carton boxes and also separated by the plastic dividers. So for this kind of scenario, 80% of the fire load belongs to carton boxes and the plastic dividers is only 20% belongs to the lithium-ion battery cells. So the fire behavior is similar to the carton unexpanded plastic and the hazard categorization. Therefore, for this kind of the categorization, the sprinkler is recommended by, I believe it's by most of the local regulations for the sprinkler requirements. Therefore, only sprinkler were tested. And also, the key finding is to wet the carton boxes is the key measures to minimize the thermal runaway propagation for the warehouse cases. So lastly, coming to the conclusion. So here I would like to suggest how to apply the small scale experiment onto the large scale experiment, because as mentioned earlier on, currently most of the experiments are cell level experiment. So, but this cell level experiment, the results will still be useful if I can correlate the some commonalities between the small scale and large scale experiment. So for instance, for the cell level experiment where the agents are discharged directly onto the cells, this is similar to the EV pad level with the battery cells housed within it, and the direct internal injection method is applied. So for the module level experiment, the direct internal injection methods can also be applied to the EV pad level with the cells. Then for the module level experiment with the external spray, this can be applied to the EV pad level with modules and also the battery and energy storage system rack levels, because the way the modules and the cells get in contact with the agents between here and here are quite similar. And the warehouse storage system warehouse storage experiment is a bit unique by itself, so there's no correlation. So to conclude for the large scale, the EV pad level and the battery energy storage, the red level experiment. So for the EV pad level, I rank the cooling effect for internal thermal runaway propagation from high to low. So basically, water mist with additive has a better cooling effect than the water spray with foam additive. Where the water spray Class A form, Class F form, and a low expansion compressed air forming system has similar cooling effect. But all these are better than the NOVAC gases and the nitrogen inner gases. So for in the red level experiment, the high pressure water mist with additive appears to be the best because it can both suppress the flame and also provide the surface and the gas cooling. So if the gas-based or aerosol suppression system are used, it is suggested to be backed up by a water-based suppression system. So regarding the battery chemistry and the capacity, so to summarize from all the different experiments, the lithium ion phosphate battery the fire is easier to be suppressed, and also the battery is easier to be cooled down than the NMC, and the LCO batteries. So for the battery with higher energy capacity, of course, it is more difficult to suppress and also more difficult to be cooled down. And it also require more volume of the extinguishing agents to put out the fire and control the thermal runaway. And lastly, the early activation of the fire suppression system is always preferred. Therefore, sensitive smoke detection system or a good battery management system are required to detect the abnormal temperature or abnormal early development of the fire, and to activate the fire suppression system as early as possible, so that it will control the temperature threshold below certain points. And for the future works, as mentioned earlier in the cell level experiment, there are some synergistic agents that are currently only tested in the cell level experiment. So these tested agents appears to be quite effective. Therefore, moving forward, all these synergistic agents can be further tested in the PEC or the REC large-scale experiments. And more direct internal injection experiment can be conducted for the REC level experiment, but it is not easy because the extinguishing pipings, tubings need to be connected into the battery rack or battery module. So this will require the system design between the fire manufacturers as well as the battery manufacturers to integrate the system together. Yeah, so for the last point, for the EV experiments, because the EV travel on the road throughout year in different seasons, so it's subject to the extreme temperature condition like the hot days in summer and the cold days in winter. So the extreme ambient temperature conditions need to be factored in during the testing of the different extinguishment agents. Like for instance, the ambient temperature on the extreme side can be from maybe negative 30 degree to the 40 or 50 degrees C. Yeah, so yeah, that's all for my sharing.
Thank you very much. Maybe we can open some time now for questions. So if anyone wants to ask a question to Linfan. Assad?
Good afternoon. Can you hear me?
Yeah.
Thank you very much for your presentation. My name is Azad. I'm a PhD student from Polytechnic University of Turin in Italy. I have a very short question. I'm wondering if you can tell what was the most common abusement method in the literature, mechanical, electrical, or thermal? Thanks.
Okay, from the literature, most of the experiments they are using the thermal abuse to initiate the fire. That means they are using some kind of the electric heaters, the flame heaters to simulate the thermal runaway. But in the actual scenario, like for actual scenario where those fire happens, like for instance the electric vehicles, so majority of the fire started when the vehicles are are being charged in a depot. So if the fire is due to the charging, so I can say this is due to electrical abuses. But one thing to add on is for the electrical abuses, it will not happen over the night. It's actually throughout a period. So maybe let me share this graph. This graph is from another research paper. So you see for the electrical abuses, actually is over the long time. The separator is being damaged due to the maybe the overcharging, overcurrent. So after a certain period of time, the separators is degraded. That's why. So one day, all of a sudden, when the vehicles is in charging states, then the fire all of a sudden it happened. Yeah. So in terms of the mechanical abuses, it is like, for instance, for the battery energy storage system, the mechanical abuses will seldom happen because that is stationary. So there's no external impact or external force. So mechanical abuses will mainly happen for the electric vehicles, for instance, if there's any car crash. So yeah, I'm not too sure I answer your question.
Yes, sure.
Yeah.
Thanks.
Thanks. Roy, you have another question?
Yeah, good evening to you, Liam, and good afternoon to the people in Europe. I'm a senior fire protection engineer working from Rumble, Norway. And we've been working with a lot with BESS, and we also are on our second battery factory building as well. So this is, of course, of very much interest. I just have a quick question. You mentioned the category with water mist and with additives.
Yeah.
Do you have a list of, or is that in the report, of what kind of additives those are? Because
Yeah.
and then the reason I'm asking, I will finish. The reason I'm asking is that I'm lacking the specific of F500, which has been tested by the Beijing Fire Research Laboratory with very good results, as well as Newcastle University did also test both last year. But I'm just wondering what the additives are in your report.
Because I'm not the chemistry background, so in my reports you can read my thesis. Actually, I listed all the additives from the cell level experiment, module level to the red level, and the pad level experiment. So you can find the combination of the different additives in my thesis report. But of course, the one you mentioned, the F500 has been tested. If I'm not wrong, it's been tested by both DNV and the RISE in their large-scale experiment. So other different kind of the additives with the different combination of the additives actually been tested in the cell level experiment.
And can I bother you with a last follow-up question on that? So based on what you presented here, cooling, you can draw the following conclusions.
Yeah.
Cooling is the most effective way to deal with propagation.
Yeah.
Water is the best to use for cooling.
Yeah.
And when I was looking at the chart you had, I understand why Novik is being used in many cases. It's a water-free alternative, but I saw that it kind of came off halfway in the cooling spectrum between water and dry powder. So would you say that then that Novik doesn't really have a high cooling effect, as Novik themselves say that it has?
Okay, I don't know whether you read the news, the Arizona cases, the battery energy storage system, the one called Fire, they are using Novak gas. So if Novak has the good cooling effect, then the fire or the firefighter shouldn't even get injured due to the fire, you see. So true enough, because in those experiments, the researchers are using thermocouple to monitor the temperature decrement when the agent been discharged. So definitely the Novak has less cooling effect compared to the water-based agent. Yes, it is. Novec can be better than the dry powder or the inner gases like CO2 and the nitrogen, but it is definitely not as good as the water. So if let's say we want to do the fire suppression, yes, Novec is very good. It can suppress a fire quick. But in terms of the cooling, in terms of to control the thermal runaway, Novec is not ideal. That's why just now what I share, like for instance here, the researchers start to combine the Novec with water mist, the Novec with other kind of the composition, which is basically to increase the cooling effect of a Novec.
So it's a good first run up where you have water as the backup alternative. So whenever you cannot deal with the Novec, then you use water. But
not really is the backup. In this experiment, they combine the two. That means they mix the two agents together in a single cylinder, or they connect the tube to the common nozzle. So when the nozzle being discharged, it discharge both Novec and the water mist together.
I got it. Thank you.
Yeah. So others, like there's one recommendation by DNV. So in DNV, probably their idea is they want to put up the fire fast. That's why they can use the Novec or aerosol as the first line of the defense. So there are sensors to continue to monitor. If the fire reignites, then the sprinkler or water-based system will come next. There's other alternative as well.
Thank you. We have a question from Jerry Jensen in the chat. He's asking for the internal application if it requires piercing nozzles or prefabricated connecting tubes.
Yeah, you are right. It is less practical, but in the electric vehicle battery packs, there are already some kind of the integration. That's why just now the conclusion part of my my summary, I mentioned this requires the coordination between the fire manufacturer and the battery manufacturers on how to integrate the two systems together without compromising the performance of the battery itself. Yeah, you are right. It requires the piercing. So if the two suppliers fully stand alone, so this system will not work. This system will only work when the two manufacturers come together. This is my view, but I don't know in the reality how are they going to so-called to cooperate on this. But of course not for electric vehicle, because electric vehicles, the electric vehicle manufacturer, maybe they are the one who take the lead to integrate the two systems together. But for the battery energy storage system, normally the different contractors or different suppliers will just perform their own installation. So maybe for the battery energy storage system, the internal application may have the long way to go. Or maybe for that cases, the owner of the battery energy storage system, they are okay to sacrifice one rack maybe. So if this sacrificing of the one rack will cost lesser than the tedious coordination or redesign process, probably the owner will just go with it. This is my view.
That's fine. Thank you.
We have another question in the chat from Peter. Is it
detrimental effect of the conductivity of water? So the answer is yes. That's why in the conclusion I didn't say okay, the sprinkler is water, sprinkler is definitely is the no. The sprinkler definitely will have the detrimental effect as you mentioned, but when the water mixed with additive, some of the additive will deionize the water mist. That's why if the water mist been deionized, it will not have the, or will have less detrimental effect of the conductivity. Yeah, this is what I found from those the research papers.
Thanks. We have another question, Antonio.
Yes, I'm Antonio from Danfoss Fire Safety. Just wanted to ask you about the duration of the application of the extinguishing agent. So how much important is the discharge duration? Is it recommended a cylinder-based system, or it would be better a pump-based system?
Okay. My scoping review didn't extend to this, but for instance, the for the electric buses application. So based on the current design of the electric buses from different manufacturers, that was from the one of the technical report published by RISE. It says the maximum carrying capacity on an electric bus is up to 13 liter the cylinder size. Then for the energy storage system is largely depends on the design of the battery. So probably the battery manufacturers need to advise like what kind of the fire load from their single battery rack. So from there, the fire manufacturer need to design for the appropriate size of the suppression system accordingly. So often I didn't find any formula or correlation between the capacity of the extinction agents versus the type of the protected areas. So maybe this will need some design coordination later on in the real application.
Thank you.
Thanks. Do we have any more questions? Guillermo?
Yes, Lucia, thank you, and good afternoon, and Linfan, thank you very much for that presentation. I'm from ABS, Guillermo Calderon, based in Houston. More than a question, just a comment. I think the presentation is pretty much in line to what we've seen on different installations. Currently, the requirements, DIMO requires a water-based system, right? And that's what we've seen so far. We are currently in the discussion on what will be the applicable requirements for electric vehicles, and that's what kind of the big question right now, because it's different when you think about the containerized energy storage system versus electric vehicle. Then we're thinking about maybe for a container carrier, you need to have a CO2 plus a water mist system. So that's what we're currently working on right now. Kind of taking advantage of the cooling effect, and but asking those two systems on an enclosed containerized ES energy storage system. The thing is that you have the enclosure that helps you kind of somehow contain the runaway, right? Thermal runaway.
Yeah.
So, and then we've been having a lot of kind of when you look at the requirements is a bit gray in that area for the containerized system, because it says that you need to have, I mean, the manufacturer is the one that will recommend this type of system. But during several risk assessment, we found that you need to have a water-based, and yeah, it's a water-based system. I've seen the aerosol system. I've seen the CO2 system for that one, but just when I look at your presentation, you just made me think about the more than the containerized system, more about the vehicle carrier vessels that that we should ask those two systems, the CO2 plus the water mist for the e-vehicle. So thank you very much. It's just more than a question, just a comment. It made me think your presentation and very well developed. I really like it. Thank you very much.
Thank you.
Thank you. Anyone else would like to have a last question?
The impact on environment.
There is a question from Elena. Have you seen any information on impact?
Okay. Just now I didn't mention during my methodology, the filtering process. Actually, I already filter away those research using the Halon and the FM200, which are going to be obsolete due to the environmental unfriendly. So for those water mist with additives, so far no, I didn't see there are further discussion on how this additive will impact the environment. But yes, the Halon and the FM200, I didn't include it in my scoping review. I filter away those papers.
Thanks. And last question from Peter. Dutch regulations are considering total flooding of containerized systems. Have you seen this before?
As I seen the actual installation, or Peter, can you clarify? Because for the total flooding from the containerized system, majority of the large scale experiment conducted is actually using total flooding, because there's no other way. The other way is there's only 2 experiments using the direct internal application, but majority of the experiments were conducted using total flooding system. So, like for instance, the experiment performed by DMV by FMUL, they are using total flooding system for the containerized system.
Okay, thank you very much. And we have to finish here. It was really interesting presentation. And yeah, thank you for all the questions as well from the audience. And